Okay, so in this video, we will use the simplex method to maximize the objective function, p equaling 2x plus y plus 3z, subject to the following constraints. So here's the first constraint, second constraint, and as always, all the variables must be non-negative. And here again, the simplex method is the better option, as if we try and solve this problem geometrically, as we have three variables, we would be in the three-dimensional space, and these inequalities would give us planes, and so combined together would give us a solid, and we'd have to find the vertices of this solid and then evaluate our objective function at all the vertices, and in this way we would find which vertex yields the maximum value of p. Well, this sounds like a lot of work. We can do simpler with the simplex method. The first step, as always, is to transform the inequalities into equalities with the help of our slack variables. So here we have 3x plus 4y plus 2z, and this is at most 12. Well, again, if we add just the right amount to the left-hand side, we'll be able to attain exactly 12. So if we add, say, s1, then this will equal 12. Second inequality, same thing. So here x plus 2y plus 2z. And again, the left-hand side is at most 8. Well, if we add to the left-hand side just the right amount, we'll have it equal to 8. And so, of course, the amount that needs to be added to this inequality may differ from the first inequality. So we have to add a second slack variable. And, as always, we have to transform our objective function. We always leave p as is, and we send everything onto the left-hand side with the objective function p. And so all of these will become negated. So negative 2x, negative y, negative 3z, plus p is equal to 0. And now we can construct the initial simplex matrix. So the variables x, y, z, the slack variables s1, s2, and the objective function p, as always, we separate the rows coming from the inequality, so the first two rows, with the row coming from the objective function. So the first row becomes 3, 4, 2, 1, 0, 0, 12. Row 2, 1, 2, 2, 0, 1, 0, 8. And the third and final row, negative 2, negative 1, negative 3, 0, 0, 1, 0. So now we're good to go. As always, we single out the largest negative entry in the bottom row, look up to the two positive entries here, and we have to construct for each one the ratio of the constant term over the entry. So let's do 8 divided by 2, which gives us 4. For the other entry, 12 divided by 2, which gives us 6. And if you remember, we choose the positive entry that yields the smallest ratio of the constant term over the corresponding entry. As 4 is less than 6, we choose the entry 2, and we now have to transform 2 into a pivoting 1 by obviously multiplying row 2 by 1 over 2. So we can recopy row 3 and row 1 as we are not changing them. And now multiply row 2 by 1/2. So we'll have 1/2, 1, 1, and circle this 1 as it is not just any 1, but a pivoting 1. And now we use this leading 1, or this pivoting 1, to kill the entries both above and below. So we will do row 1 minus 2 row 2, row 3 plus 3 row 2. So let's perform now these two operations. So we can recopy the second row as it is the only one that we're not changing. Now let's apply our operations. So first, row 1 minus 2 row 2. So 3 minus 2 times 1/2 is minus 1. 3 minus 1 is 2. 4 minus 2 is 2. 2 minus 2 is 0. 1 minus 0 is 1. 0 minus 2 times 1/2, 0 minus 1, negative 1. 0 minus 0 is 0. 12 minus 2 times 4, 12 minus 8, 4. Second operation, row 3 plus 3 row 2. So negative 2 plus 3 times 1/2 is 3/2. But negative 2 is negative 4 over 2 plus 3, negative 1 over 2. Negative 1 plus 3 times 1 plus 3 gives you positive 2. Negative 3 plus 3 is 0. 0 plus 0, 0. 0 plus 3 over 2, 3 over 2. 1 plus 0, 1. 0 plus 3 times 4 plus 12. And there we go. So this completes the first step of the simplex method. And now we look at the bottom row. If all the entries were non-negative, it would be done and we would have obtained the optimal solution. But as there's one leftover entry that is negative, we have to repeat. So we would single out the larger negative entry in the bottom row, as there's only one, not much of a choice. And now again we have to consider in the column above the ratio of the constant term over the entry if that entry is positive. So here we'll have 4 divided by 1/2, which gives us 8. For this entry, we'll have 4 divided by 2, which gives us 2. Well, the smallest ratio is clearly 2, and so we now turn this entry into a pivoting 1. Of course, by multiplying row 1 by 1/2. Let's perform this operation. Or actually, let me recopy row 2 and row 3 as we're not changing them. Always circle your pivoting 1. And now we multiply row 1 by 1/2. So 1, pivoting 1, 1, 0, 1/2, negative 1/2, 0, 2. Now that we have our pivoting 1, we use it to kill the entries below. So we'll do row 2 minus 1/2 of row 1, and row 3 plus 1/2 of row 1. So let's perform these two operations. We can recopy the first row now, as it is the only row that we're not changing in this step. Okay, so first operation, row 2 minus 1/2 of row 1. So 1/2 minus 1/2, 0. 1 minus 1/2 1 half. 1 minus 0, 1. And this is still a pivoting 1. 0 minus a half times 1 half is minus 1 quarter. 1 half minus a half times negative a half is plus a quarter, but 1 half is 2 over 4 plus 1 over 4, 3 over 4. 0 minus a half times 0, 0. 4 minus a half times 2 is minus 1, 4 minus 1, positive 3. Now we do row 3 plus a half row 1, so negative a half plus a half is 0. 2 plus a half times 1 is plus 1 half, but 2 is 4 over 2 plus 1 gives us 5 over 2. 0 plus a half, 0 is 0. 0 plus a half times 1 half is 0 plus 1 quarter, 1 quarter. 3 over 2 plus a half times negative 1 half is 3 over 2 minus a quarter. But over 4, this is 6 over 4 minus 1 over 4, gives us 5 over 4. 1 plus 1 half times 0 is 1 plus 0, 1. And finally, 12 plus 1 half times 2 is 12 plus 1, 13. So this completes our second step in the simplex method. And if you look now at the bottom row, all of the entries are non-negative, which means that we have achieved the optimal solution. Well, what is it? Let's remind ourselves that this is the column for x, y, z, s1, s2, and the objective function p. So how do we, if you remember, read off the final simplex matrix in order to get the optimal solution? Well, we have two types of variables. We have the basic variables, the variables that in their column contain a single pivoting 1 where all other entries are equal to 0. And we have the non-basic variables, the ones that don't have a pivoting 1 where all the other entries are 0. So if you remember, we set the non-basic variables equal to 0. So y is non-basic, so we set y to be equal to 0. S1 is non-basic, so S1 is also set to equal 0. And S2 is non-basic, so S2 is also set to be equal to 0. Now if you think back to the rows being equations, well, as all of the non-basic variables are equal to 0, we can ignore these columns, as we would get plus some real number in each case times 0, which is 0. So these no longer affect our equations now that we've set them to be equal to 0. And so we can ignore them. And now we can use the pivoting 1 to solve for the corresponding basic variables. If you look at x, x equals 2. Z equals 3. And P equals 13. And we're done. So if we write our conclusion, the maximum value that P can take occurs when x equals 2, when y equals 0, and when z equals 3. And the maximum value that P attains is 13. And that's it. Now we can do a quick check to see at least if these values are consistent with the value of P being 13. If you go up, the objective function P was 2x plus y plus 3z. So let's just check it for good measure. So our objective function was 2x plus y plus 3z. So we can replace in the objective function by the corresponding values, and we'd get 2 times 2 is 4, plus 0, plus 3 times 3, 9, and of course 9 plus 4 is 13. So this is simply a quick check to see that it is at least consistent with the objective function.